Okay, good morning. That was really, really sad. Good morning. Much better. Okay, so exam 3, you should see your score on WebAssign soon, if not there already. If you don't see it yet, nag your TA about it. And if nothing happens, tell me. 90, 80, 60, 40 are the cutoffs for this exam. And I average all the cutoffs on the 3 exams, so just so you can get some kind of idea, with 3 exams put together, where you stand right now. 270, 240, 185, 140. That's out of all 3 exams combined. All right? All right, so today we're going to continue with Chapter 10. We'll look at Section 10.2. Last time we saw what to do with parametric equations and how they could help us sketch curves. Today we're going to do some calculus with those things. This is a calculus class after all. The first thing we're going to look at is the slope of the tangent line. All right, so if I got some kind of curve like that, then suppose we want to know the slope of the tangent line at some value x is equal to a. Normally, we simply take the derivative and plug in x is equal to a, right? But in parametric form, both of these variables are functions of a third variable. We'll call that t again. So we need to first find a way to calculate a tangent line slope with t as the variable. So we need that formula. If we know y as a function of x, for example, y is equal to x squared, then dy dx is 2x. Well, that's easy. But what happens when x and y are both functions of a third variable? Obviously, this is going to be a little bit more complicated because the formula now has got t all over the place. We have to modify dy dx to get the formula for the slope. So we're going to go back to earlier calculus. So recall from Calc 1, we know by chain rule, dy dt is dy dx times dx dt. Right? So that what happened back then was that we had y as a function of x, but x in turn is a function of t. So if you wanted to relate y to t, we take the derivative dy dx first, and then dx dt. Right? Now, we're going to modify this a little bit. we really, really want to know right now is what dy dx is. And we got two pieces with t in them. If I divide both sides by dx dt, then I'll get dy dx is equal to dy dt over dx dt. So that formula is going to allow us to find out the slope if both x and y are functions of t. All right, so looking at this formula here, what do we have to watch out for? What's one thing that's going to make this formula go stupid? Right. So this formula is only valid provided that dx dt is not equal to 0. Right? Now, if that happens, then we got a problem, and we'll deal with it when that happens. But for vast majority of the things you will see, even in applications, this is going to be good enough to get you the slope. Okay, so a simple example. Let's look at a circle with a radius of 1. Let's find the slope of the tangent line when t is equal to pi over 2. Okay, so now I got x and y both in parametric forms in function of t. To find the derivative y with respect to x, we use that formula here. dy dt is cosine of t. dx dt is negative sine. So dy dx is cosine t over negative sine of t. Then we'll look at what happens at pi over 2. And we get 0, right? And that makes sense, because what are we looking for? Here's my circle, right? I want to know the slope of the tangent line when t is pi over 2. So that's right here. And as you can see, just by looking at it, the tangent line is horizontal. It's going to give you a slope of 0. Now, what happens at t is equal to 0? What's the slope? What's the slope of the tangent line at t equal to 0 or pi? Undefined. And in that case, you see what's going on with dx dt. That's at 0, right? dx dt is 0 at here. So we're dividing by 0, and therefore this wouldn't give you a meaningful result. You have to recognize that we have vertical tangents. All right? So that's what happens when you run into dx dt equal to 0. Try to draw a sketch and verify that you have. Most likely it's like this when you have vertical tangent lines, when the slope is undefined. Questions? No? Okay, good. Now let's find out the second derivative. So first of all, let me rewrite this formula here. Oops, that's an x. Now suppose we want to find out the second derivative, or the third, or the fourth, and so on. If you know how to find the second, you know how to find everything after that. And what we can do actually is to take advantage of that formula here. One way to look at this formula is this way. Think about what the formula is telling us. If I want to know the derivative of something with respect to x, on the right-hand side, that something shows up in the numerator. If you consider the second derivative as d dx of dy dx, then what we can do is to reuse that formula here, but change y to dy dx, right? So therefore, we get d dx of dy dx, which is the second derivative. And according to the formula here, on the right-hand side, there's only one y, and we change that to dy dx. And that's d dt of dy dx over dx dt. And once again, the same restriction applies. Dx dt cannot be 0. So really, these are the same formula, right? And if you want the third derivative, carry out the same procedure, the fourth, the fifth, everything beyond that, exactly the same idea. It's very tempting to see the formula at the top here and extrapolate it incorrectly and get this quotient here. This is not true, right? We cannot just take the derivative up and down. This is what we have to do to carry out the derivative. Okay, so let's go back to that circle and try this out. We want to find the second derivative, again, at pi over 2. First, let's redo this first derivative, dy dt over dx dt cosine of t and negative sine of t, right? Right, we did that already, nothing new there. Now we find the second derivative. Again, remember that by reusing this formula here. Oops. I want the second derivative, so dy dx. There we go. Right? In that formula, we get y out and put in dy dx in the place that y used to occupy. All right, now we need the derivative of dy dx with respect to t. Right? So we take the derivative of that. We'll use the quotient rule here. This thing squared. And downstairs is still dx dt. So this guy again. Okay, so once again, numerator is the derivative of this. And this is the quotient rule. Right? And you see what the numerator of the numerator is? Sine squared plus cosine squared, which is 1, yeah. So that's good. 1 over sine squared of t over that. So at t equal to pi over 2, we get 1 over negative 1, negative 1. Okay? Now, do you remember the geometric significance of the sign of the second derivative? What does it mean when it's positive? What does it mean when it's negative? The concavity, right? Yeah. So this is negative, so that means what? Concave down. Yeah. Let's look at the shape. We are right here. We had a 0 first derivative, of course, and then look at the shape. Circle opening down, right? So it makes sense that we have a negative 1 because we're sitting at a concave down location. Yeah? Yeah, you could do that. And take the derivative. Yeah, exactly. You could do that too. And that will actually get you directly to here, to cosecant square. So of course, yes, you could do that. Other questions? All right, now let's do another one. All right, so we got x is e to the t, y is t, e to the minus t. So now it's much harder to sketch this thing, at least easily. So we have to rely entirely on doing the steps to get these things without having to look at the shape. So once again, we start with the first derivative. dy dt. I need the product rule here, right? So first times the derivative of the second plus derivative of the first times the second. dx dt, that's easy, e to the t. We're going to have to differentiate this again for the next step. So let's simplify this as much as we can before we move on. Pull out the e to the minus t, and then I have a 1 minus t all over e to the t. And now I can write this as e to the negative 2t. If I bring this up, I could also take this down. Either way is fine. If I do this, the next step would involve another product rule. If I take this downstairs, the next step would involve a quotient rule. It's whatever you prefer and whatever you want to stay away from. Now the second derivative is the same formula. Remember, it's the same formula with this y turned into dy dx. Numerator is the derivative of the first derivative with respect to t, so a derivative of that. One more application of product rule would be good. First, derivative of the second plus the second times the derivative of the first. dx dt is downstairs again, which is still e to the t. And let's simplify this too. Let's factor out e to the minus 2t from upstairs. Minus 1 plus negative 2 times 1 minus t all over e to the t. So here we got 2t minus 2 minus 1, 2t minus 3. And then again, I'll bring this back up. So there we go. So once again, you can use that to find out the shape of the graph at one point. We can choose any value of t. You can find out the slope and also the concavity and kind of get some idea of what the graph looks like at that one place. Questions? Nope? Okay, good. Now let's look at how we can calculate the length of the curve. And we looked at this earlier. Right, we had this form of calculating the length of the curve, square root of 1 plus dy dx squared dx. This is saying that x is between a and b. We could also do that, right? That's when y is between c and d. And back then we had two choices. We could use the top one if we had y expressed in terms of x, and the bottom one if x expressed in terms of y. When integrating vertically is easier. So we had these two forms to work with. Now we're in the parametric world. We're no longer tracking x and y directly. Right? Now we're counting things in terms of t, in terms of time. We're not counting x or y directly, at least. So now I want to know, what does that formula look like if, let's say, t is bounded between a and b? It'll probably look a lot like that with an integration of some sort, but obviously these two forms are not useful the way they stand right now. Instead of working with the old forms the way they stand, let's go back to where they came from. And then maybe we can construct a new formula from there. All right, so remember, the way we did that was we chose 2 points on the curve. We wanted to find the length of that curved portion. So what we did back then was we drew a straight line, and then we kind of approximated that. Right? So that was the approximation. If we bring the 2 points together close enough, then eventually we'll get the right answer. But the first order approximation is like that. We want t to get into this expression and not x and y. So what we can do here is do a little bit of algebra. we're going to divide both of these by delta t. So I divided both of them by delta t, but they're squared. So we really divided everything by delta t squared. And to balance that, we'll multiply a delta t squared back under the radical sign. And now we'll take this delta t square out of the radical. It'll lose the square, so it sits out here. And now these two expressions are identical. The first one, we're tracking little incremental changes in the distance. The second one, we're using velocity, and then multiply by time. We know the distance is velocity times time. So we're really finding a velocity as we move from here to here, multiplied by how much time it took. So they are equivalent. And now to make this precise, we take a limit. We take a limit, now we shrink time. That's equivalent to bringing the second dot closer to the first. And the closer they get, the better the approximation. And in the limiting case, it becomes exact. So this becomes dx dt. That becomes dy dt. And delta t becomes dt. That's going to give us one segment. If we want the whole thing, then we integrate over the time, right? A to B. So I start at time equal to A, and at time equal to B. So there we go. There's the formula to find the length of the curve when x and y are in parametric forms. Velocity, velocity. This whole thing before dt, that's a velocity. Velocity times time gives you distance, or the distance you traveled. And that's the way to understand that formula. All right, so let's try this on something. Let's find out how long this curve is when x is expressed as e to the t plus e to the minus t, and y is 5 minus 2t. T goes from 0 to 2. Okay, we got almost everything we need in the formula. We know the range of t. That's going to become the integration limits. And then we just need a first derivative of each one of these, and then throw that into the radical. Dx dt, e to the t, minus e to the minus t. Dy dt is negative 2. Then we integrate 0 to 2. Those are bounds of t. that thing squared plus that thing squared, all under a radical. We'd integrate with respect to t. Let's work underneath the radical here. This thing squared, multiply that out, is the first thing squared minus 2 first and second, and then the last thing squared. Right? In the second term here, e to the t times e to the minus t, that becomes e to the 0, which is a 1. So this is really e to the 2t minus 2 plus e to the minus 2t plus 4. Or e to the 2t plus 4 minus 2, that's plus 2, right? And then plus e to the minus 2t. And now I'm going to do a little bit more of the algebra here. I'm actually going to put these two things back into here. So I'm going to purposely rewrite it this way. All right, do you recognize what's underneath the radical? Compare this to the first three terms here. The only thing different is that sign here. So where did these three things come from? From this, right? So what would this turn into? With that, what changes between, what does that change do to this? Everything is plus here. So that would be a plus, right? Yeah. So this is turns into e to the t plus e to the minus t, the whole thing squared, under a radical. And you can verify that by multiplying this back out to get to here. Yeah. Plus 4 and minus 2 turns into plus 2. Right? This is 1, so that's a minus 2. That's a plus 4. 4 minus 2 is 2. It's now what? No, but regardless of the value of t, e to the t times e to the minus t is 1. Right? That's 1 regardless of the value of t. Does that make sense? Yeah. Okay. Question? How I went from here to here? Or oh, okay. Yeah, same logic. I recognized that this was a 1, so I took it away to simplify. And then I look at this. It's looking suspiciously like something squared. And in order to make it look just like that, I brought it back in. Because that's a 1. I can multiply anything by a 1 without changing the expression. Other questions? Okay? All right, so now we can integrate this after some magic, dark magic. No, it's the magic you know. Yeah, it's magic, fine, but it's the magic you know. Now we can integrate this, right? E to the t minus e to the minus t, 0 to 2. So that's e squared minus e to the minus 2 minus 1 minus 1. That's a 0. So we get e squared minus 1 over e squared. All right, so that's how long that curve is. Okay, questions? All right, let's do one more. Okay, now this one is fun. You got some kind of object. It's traveling on a path described by the parametric equations x is equal to cosine squared of t, and y is equal to cosine of t. And t is between 0 and 4 pi. We want to find two things. One is the length of that curve. The other one is the distance traveled by that object. Now, upon first glance, you would think they're the same thing, but you'll find out why they're not the same thing. First, let's find out what exactly that curve looks like. So I'm going to choose a few values of t here, just convenient values. So I chose t is pi over 4, pi over 2, 3 pi over 4, pi, and then 5 pi over 4. And then plug these into x and y here. We'll see these numbers for x and y. 1, 1. 1 over 2 over 1 over root 2. 0, 0. 1 half. Minus 1 over root 2. 1 minus 1. 1 half minus 1 over root 2. When t is 0, we start at 1, 1 right here. When t is pi over 4, we go to 1 half, and 1 over root 2, that's a little bit over 0.7, somewhere over here. And then pi over 2, we're at 0, 0. And then 3 pi over 4, we're down here again. Pi, we're down here. So it's a parabola opening to the right. And now what happens here is this thing is just traveling back and forth on this path. Starts at t equal to 0, ends here at pi. And then when t becomes greater than pi, right here, this is just retracing the steps again. So this becomes that. So it's going backwards. So when t is 2 pi, it would be over here. 3 pi, and then 4 pi back here. So just moving back and forth on this parabola that opens to the right. Back and forth. Right? Now, do you see why the distance and the length of the curve are not the same thing? Yep. If I stop time at pi, then they would be exactly the same thing. But because I'm going beyond that, the length of the curve is that. The distance traveled is simply 4 times the length of curve, right? So that's the way we'll do this thing. All right, so let's calculate the length. So if I want just the length, where do I stop? Pi, right. And now the derivative of x, negative 2 cosine t sine t squared, and then derivative of y minus sine t squared dt. Okay, so now more magic. That's not something we can integrate very easily. I'm going to factor out a sine square and then bring it out of the root. Like that, okay? Then I'm doing a substitution. And this turns into radical 4u squared plus 1 times negative du. And then the bounds I'm changing by that. Now we still can't integrate that. There are 2 ways to do from here: trig substitution or look up an integration table. And table is probably the easier way to do that. So integrate by table, entry number 21 in our book. And that's going to give you something around 2.9579. Right, so that's how long that path is. Now, how do you find the distance traveled by that object? How many times does it traverse that arc? 4 times, right? So 4 times L, which is roughly 11.8315, right? So the road is only this long, but it travels on the same road 4 times. So it really travels that much distance. All right, that's it for today. See you Friday. get email directly from me, but you can go to this other website to download it.
Okay.
So that's what you want to do. Send it to me.
Okay, that would be great. Thank you.
Yeah, I was just checking over that. So for the last one now, because what we're saying with the oscillating back and forth is that the values for each source of the function, values are in that denominator.
Go back to the Cartesian equation, that's x equals y squared.
Yeah.
So then in that case, you gotta recognize the bound.
Yeah, but the oscillation here, like back and forth,
Right.
was really more what I was looking for. It makes sense.
Right, so okay, this is what you can